Okay, let's go ahead and get started. So a couple logistical items. Homework 9 is out now. So that's due next week. And basically that's going to be making a tic-tac-toe player and also connect 4. So we're going to be using a technique we talked about today, Monte Carlo tree search in order to do that. Quiz 9 is postponed, or really gotten rid of, in the sense that we don't have a quiz next week since we're going to have a midterm anyway. So no quiz. Homework 9 I said is out. That's not a program assignment. It also happens to have to do with tic-tac-toe and does have to do with Monte Carlo tree search, which we're going to be talking about today. So this is on Monte Carlo tree search. The program assignment is also on Monte Carlo tree search and has to do, as I said, with implementing both tic-tac-toe and connect 4. If you've never played connect 4, don't worry. It's simple rules available on Wikipedia. The midterm. So midterm 2, I realized, so I was a little concerned of people not having both printers and scanners, and I know a fair number you do, and that's great. But I think the best approach for this is going to be to give you a PDF, printable PDF of the midterm on Monday. And then you have your choice of how you want to do that. So you can either print it and then go ahead and fill it out by hand and then scan it back in and submit it on Gradescope. That's one thing you could do. A second thing you could do if you had, let's say, an iPad or a tablet of some sort is just take the PDF, go write your answers to it on your tablet, and then upload that PDF to Gradescope. And then the third alternative would just be take the PDF, read it online, and then create your answers in something like Microsoft Word or LaTeX or something like that. And then go ahead and convert whatever that is to a PDF and upload that. So go ahead and the last one is sort of my last choice, but it's certainly very possible, is just write your answers in Word.
I have a concern about that.
Go ahead.
Which, as someone in that third group who doesn't have access to a printer or a tablet, I feel like it will take extra time to have to pick up answers.
So that's a good point, and I am going to be adding extra time. I just don't want it to be time constrained. So I figure I will make it, double it to something like 4 hours, which just makes sure no one has any limitations with respect to that. And then, of course, that timing would only, the time would only be measured on you actually creating the answers. So the creating the PDF, the scanning, the whatever you need to do to send it up to Gradescope doesn't count as part of that time. Does that address your concern, Shannon?
Yeah, thank you.
Okay, very good. So I will make a Piazza posting over the next day or two so that everyone gets the information about the midterm, including those who aren't in class right now. Other questions about the logistics? All right, so let's go on finishing up this chapter. And to my mind, the most exciting topic today is Monte Carlo tree search, and we're going to be finishing up the class today with that. Monte Carlo tree search really is the basis, for instance, of AlphaGo, AlphaGo 0, and so on. So let's go ahead and get started. So we had just left off on Monday talking about expected updates versus sample updates. So sample updates, sorry, I had a little bit of typo here. So this is computation with a T. So a sample update, if we look at the backup diagram, right, we have something like S and A. We go ahead and get a reward and a new state. And then we take the max over all this, right? So that's just Q-learning. If we look at an expected update where we actually have either explicitly probabilities from the environment or we have a model which has probabilities, then we can go ahead and do an expected update. So here we have, so this is the sample. And the expected, we have our state and action, and then we go ahead and using the probability P, go ahead and do a weighted sum of, or a weighted average over all of these S primes. And then for a given S prime, we go ahead and take a max among all those Q of S primes, whatever those A's are. Okay. So in the sample update, we're doing a single maximum across actions, right? Whereas in the expected update, we're doing this max for all S prime R pairs, right? So basically this branching factor that we have here in terms of how far that branches out tells us how many maxes that we need to do. Okay, if we've got just 3 as we had here, then it's really not much more expensive, right, than doing a single max. We do 3. But if we had a large branching factor, 1,000, 10,000, something like that, then this expected update could be very expensive, right? So this expected update could be expensive. And if we look, the cost of doing that computation, right, if we take into account how many maxes that we are doing, let's just look at this worst case branching factor of 10,000. Okay, so we got 10,000 branching factor from our S comma A. And so we've got to do then 10,000 max A primes in order to do our weighted average. And so what we end up with is basically this, sorry, let me do highlighting one moment. Let me at least do this. So we have here our RMS error. Basically, we have not updated Q of SA until we do 10,000 computations, and then our error goes down to 0, assuming the Qs for the subsequent state action pairs are actually already correct. Okay, so do 10,000 computations, and then we got the correct value. Another alternative would be to do sample updates instead. And if we do sample updates, right, if we do one sample update, we'll reduce the error a little bit. We're way up on the top left of the curve here. But as we do more sample updates, we're going to start reducing the error. And in fact, we can see in this particular graph, this was for a particular experiment, but in this particular graph, we can see that by the time we've gotten down to, what is it, maybe, I don't know, 5% of our way across this graph here. Okay, so that would be something like 500 computations. That our error is fairly low. And so it's not clear it's worth having done those 10,000 computations just to update this one state for a couple of reasons. One, we can go ahead and update this state to be close to 0, although not equal to 0, with many fewer computations. But the other advantages are we can go and be updating other states as well. And not only that, we don't have a 10,000 computations before we ever update this state. And by updating this state and getting at least an initial estimate, that can allow us to get more accurate estimates for other states. So I guess what I would say is, if we don't care about the cost of computation at the time, then an expected update is always better than a sample update, assuming we have a correct model of the world. But if we do care about those computations, then this branching factors really starts to matter. And there, it may be more effective to go ahead and do sample updates. And again, some of the reasons that sample updates are better, or can be better. So one reason is we more quickly update Q of SA, which allows other updates to be more accurate. Right? And a second is just that we can approximate more, let's say, Q values in the time it takes to do one expected update. Questions on this topic? All right. Let's look at this uniform sampling. So this uniform sampling, let's look at looking back to, let's say, DynaQ, or even beyond that, let's say DynaQ+. So in DynaQ+, if you remember, what we did is we would choose a state action pair at random, uniformly at random. And then we would go ahead and do a one-step update. Right, this is during the planning phase, right? In the planning phase where we might have taken one step in real life, right, in the actual environment, and then we do n planning steps, right? Where each of these planning steps, we go ahead, choose a state action pair, do a one-step update, to choose a state action pair, do a one-step update, and so on, okay? The problem with this type of sampling is we may be updating parts of the sample space we don't care about. All right, that's one possibility. Another is the fact that we may not be updating things that are changing. And we looked at how to address that with prioritized sweeping, right? The idea that we have a priority queue, which is controlling what we want to next update. And that priority queue is controlled by how much of a change that we are making in a state's value. So if we make a very small change, we don't care about it too much, that's a very low priority. If we make a large change, that's high priority because the states leading to that will want to go update. Okay. So that's one way not to do uniform sampling. Another way is some sort of an on-policy distribution. So this is trajectory sampling. So the idea here is when we're doing our planning step, rather than picking a bunch of different state action pairs all at random, go ahead and start with a start state. I'm saying a start state because your environment, we may have more than one start state, okay? So start from there and then just go start sample and then keep sampling until we either run out of time or complete an episode. Okay, now, something I want to point out, the question came up, it was either last Wednesday or last Monday, about the idea of taking episodes that we have in real life and during planning, replaying those episodes. And that's certainly of value, right? Because that will go ahead and update state values. But let me see if I can pictorially show that. So let's say we have episode 1 and episode 2. Then we can imagine that during our planning phase, we go ahead and replay episode 1, right, all the black, and replay episode 2, all the blue. But that's not quite what we're talking about here. Right? What we're talking about here in this trajectory sampling is at every point in time. So we start at a start state, right? We start, let's say here. Okay, so we'll make this in red to show this is planning. So we start here, and then we go ahead and take transitions that we know about from our model. But if we look at this state here, right, this state, actually that's not the interesting state, it's this state here, we have two possible places it could go, right? It could go sort of down the trajectory episode 2 went or down to the trajectory episode 1 went. And so we could start on episode 2 and end on episode 1. Or really we could have any odd combination of all sorts of different episodes, because each episode is just updating the model, and then we're using the model dynamics in order to be creating this trajectory. So let's look at this. Sort of an episode is a sequence of, you know, state actions from the environment. And I'm going to call a trajectory is a sequence of state action from the model. So the model did come from the episodes of the environment, but the trajectories are not necessarily one-to-one with episodes from the environment. Josh, does that make sense?
Yes.
Okay, does anyone have any questions on this? So this is a alternative, let's say, to do prioritized sweeping. It's really an alternative to either uniform or prioritized sweeping. And this is really a big question. How do we want to be updating our Q values, especially in large state action spaces, right? What is it we want to be, how do we want to be deciding how to do that updating? And we've seen uniform, we've seen based on changes, update states that lead to those changed states. And here now we've also seen based on parts of the state action space that are likely to occur. And how do we know they're likely to occur? Because they're parts of the state action space that we actually see when we start from our starts state. Okay.
So can you quickly explain, like, when would you use trajectory sampling over like prioritized sweeping? Like, can you give an example?
I think the best example would probably, so let's think about this a second. I'm trying to look at something with a large state space, a state action space. So let's look at, for instance, chess, and I'm thinking out loud right now. So, right, fairly large branch vector, it's deep, so it's a large state action space. Clearly their uniform is out, right? And so the question is, do we like prioritized sweeping? Do we like using this trajectory sampling? And so the interesting thing about trajectory sampling, right, is we are going to be ending up, we should be ending up getting to a terminal state, assuming this is an episodic task, as long as we don't have any limit on trajectory. So I guess some trajectories could be long. I don't have a good, I guess I don't have a good rule of thumb for when you would want to use one versus the other. What we're going to talk about momentarily, the Monte Carlo tree search, is really how would I describe it? It's sort of like trajectory sampling in the sense that we're going to be starting at start states and going on and generating episodes, but it's a little more principled way to be searching our search space. So I'm sorry I don't have a really good answer for you. Sometimes this is going to be whatever works best for your particular problem, right? This is, in some sense, one of the choices you get to make in terms of solving your problem. So like choosing hyperparameters and, you know, choices for alpha and for gamma, you also then have some of the questions of what actual reinforcement learning algorithm to use and what are the particular settings you want to be using on that. Before we get to this Monte Carlo tree search, just the other thing to think about is when you're doing the planning. So one possibility of doing the planning is in the background. So this would be, let's say, always. Our motto might be always be planning. Okay, is it Glengarry Glen Ross? It's always be closing, I think. So always be planning. And there we're just using whatever time we have, that we're not doing something else to be planning. I think I mentioned already the idea of our robot that's moving, you know, around in the environment. And while it's doing a movement, it's got, of course, tons and tons of time, of CPU time, that it can also be doing planning. So that makes sense. And the other one is at decision time. So when a decision is to be made, do some planning. All right, that's, now I'll tell you, I'm not much of a chess player, but I find most of my planning certainly happens at decision time. That is when it's my turn to move. That's when I end up doing most of my planning. And part of the reason for that is that a large part of my state space has been closed off once my opponent makes a move, right? So before my opponent has made a move, when I've made a move, I've got to be considering all these possibilities of what if they do this, what if they do this, what if they do this, what if they do this. And so, yes, it's still worth doing some of that, but then once they've actually made some particular move, it's much easier to focus on that part of the state space, which is the one I'm interested in right now. So I don't care about all the possible state spaces as I'm playing a chess game with someone. I care about the ones that are involved in the game I'm in right now. Does that make sense? Dave?
Yeah.
Okay. It just helps me to get some feedback. It's surprisingly lacking having just people's names up on the screen.
Yeah, it makes sense. Thank you.
Okay, thanks. All right, so let's look at, before we get this idea of rollouts, let me look at sort of our states, searching a state space. And in particular, I'm going to go ahead and ground this in the idea of a two-player competitive game. Okay, so we're going to be looking. I don't know what just happened. Okay, so we got a two-player. Competitive game. All right, and we want to look at searching a state space. I'm going to start with tic-tac-toe. Tic-tac-toe happens to have, right, a very small search space. But if we look at the actions, there are 9 actions at the top level, and then after that, there are 8 spaces that can be filled, so 9 times 8, so 9 factorial different possibilities. But let me just present this in the terms of a tree. Okay, so this is the top of our tree, right? This is X gets to make a decision of what to do. And there are 9 possibilities. So they could go at the top left, all the way to the bottom right, right? And at this point then, it's O's turn to move, and O can move in one of 8 possibilities. Say O moves there, all the way to, let's say, here. Okay. And each of these states then leads to another level of the hierarchy, unless, so let's look at one particular part of this space. So here, let's say X goes there. And then from here, O goes there. And again, there are a lot of possibilities. And then from here, one possibility is X wins, right? So this node is a terminal node because of the fact that the game is won, right? So at this point, the game is won. And that would say that the result, we'll say, is +1. Okay, so we'll say +1 from means a +1 from X's point of view, right? Since this is a competitive game, a +1 for X is a -1 for O. Okay. So here's my question. Given that our results of a game can either be +1, which is X wins, 0 if it's a draw, or -1 if X loses, Julius, when we're at this state and X gets to make a move, what's the best move they can make?
Sorry, which state are you referring to?
I'm referring to, let me see if I can, I'm referring to this state where X has 2 in a row on the left-hand column.
Mm-hmm. What's the question?
What action should they take? That is, what state should they move into to get the most reward?
The state that ends up with them getting 3 in a row.
Yeah, the state that ends up getting 3 in a row. But if we don't know anything about tic-tac-toe, what I can say is the state with the most reward, right?
Most reward, yeah.
Yeah. So let's say none of the other states at this level are going to be terminal states, right? The game only ends if I go in the bottom left. If I go anywhere else, let's say in the top center, then the game's going to continue on, right? And in fact, the game could continue on with, let's see, X, 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 O, 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 right? So this would be a reward, since O1, of -1 instead of +1, right?
Okay.
So from X's point of view, X wants the maximum of all these. Would you agree with that?
Yeah.
Okay. From O's point of view, though, O doesn't want the maximum, right? Because the maximum is getting X to win, and O wants to win. So this is for X. But at this level, sorry, so it's X's turn here. X looks at its children and see which action led to the maximum value. Here is O's turn to play, right? And the question is, what should O play? If we come up with values for these, like let's say this one is a +1, and this one is a 0, and they're all just 0s and +1s, which one should O choose?
The minimum for X.
Exactly. So we want the minimum value. Okay. So as we are deciding as X what to play, if we had values for all of these states, we could say that we wanted the maximum across all these. Within any one of these, then the next level we'd be looking at the minimum, because that's O's turn, right? So we're assuming, as we're deciding our strategy, we're assuming, let's say we don't have a stupid player, right? Let's say we have a smart player, and we can look at the entire game tree. What's the best way to play? Well, we should assume that we're going to take the best action that we can take, and once we've taken the best action we can take, our opponent's going to take the best action they can take, and that's going to go back and forth and back and forth, okay? Everything eventually goes down to leaves, right, in this state space. They're all terminals at the end, and we know either it's a +1 because X won, a -1 because O won, or it's a draw. And we can then percolate those values up a level, right? And basically say, as we go up to a higher level, depending on whether it's O's turn or X's turn, we're either looking at minimums or maximums for those, right? But as we're deciding what to do, we should never assume that O is going to play against O's interest, right? Does this concept kind of make sense? Can you see how in tic-tac-toe you can actually just generate this whole thing, go down to the leaves, and then back up and figure out what the right thing to do is. And by the way, if we look at our value with perfect players, what's the value going to be of an empty board, Julius?
Value for what?
Yeah, if I play perfectly and my opponent plays perfectly, how's the game going to end up?
One winning and the other.
Have you played much tic-tac-toe?
Kind of.
Okay, so once you have a good opponent, you'll find no one will ever win, right? You can always force a draw. So
Okay.
the eventual value up here is going to be a 0.
Rhodes, I have a.
Go ahead, Monte.
So the tree structure kind of makes sense when we think about trajectories of actions taken and states that it leads to. But do we kind of lose this sort of acyclic nature of the tree when we can arrive at states through many different trajectories?
So we could look at that in two different ways, right? One way we could look at this is, well, we can look at it as a complete tree with duplicated nodes as one possibility, or we can view it not as a tree, but as a DAG if we account for the fact that there are multiple ways to get to a single node. It shouldn't really affect in either case the computation of what we should do by starting at the leaves, assigning what that terminal reward is, and then percolating it up to the parents, either as maxes of all the children or mins of all the children, depending whether it's an X or a O, whose turn it is, player 1 or player 2.
Okay, I think that makes sense, especially if we do only like one-step backups. That definitely makes sense. But I guess even in the other case, the main thing that I'm worried about is like if we lose the fact that there's always one path to the root from a leaf, how that might affect our backup.
Yeah, well, and what I want to make clear here is right now I'm talking conceptually about states and actions leading to other states. So one thing is we assume we have a perfect model, which of course is true in tic-tac-toe. And we're going to look at moving our way through this space a little bit later. So we in fact will be looking at trajectories in a little bit. For right now, we're just looking at the fact that any perfect information game without any randomness, right? We can just look at, we have the starting configuration, and then there's a branch for how the first player can play. And then from there are branches to how the second player can play. And that continues on until eventually get to some terminated condition. And, and we, in theory, could completely analyze from the leaf back up and figure out what perfect play is, right? We don't know for chess, can the first player win? If both are playing perfectly, you know, we just don't know. But in practice, it is a finite, albeit extremely huge, tree that gets generated from all this, you know, conceptually. So we could calculate that.
Sure. Thank you.
But the fact is, for something like chess, we can't do it all, right? So we've got to figure out some way of exploring part of this state space, and not all of it. Okay. And one thing that you can do is something like just go only so deep, right? Look ahead only so many moves. Okay. I'm not sure what state of the art is in chess in terms of the hardware, Deep Blue and something like that, and how deep they can go. But, you know, it's on the order of 3 to 10, I would guess, steps ahead that one can look. And if you've, you know, played any particular game, chess or checkers or something else, you do some look ahead, right? You look and say, well, if I go here, my opponent could go here, or could go here, or could go here, and then I could go ahead and do this. What we as humans don't do is consider every possible move. So we don't consider some moves. We just figure they wouldn't be useful. And so we only look at some moves. And then in response to that, we only look at some of our opponent's moves and so on. So we do not a fixed depth branching everything. We instead do more of a focused search. And in fact, that's what the Monte Carlo tree search is going to do, this focused search. So where we kind of have promising paths that we're going to look through, that we want to investigate more. Okay. So a rollout algorithm. Rollout, this term comes from backgammon. I don't know if you've ever played backgammon. It's a fun game. It's very popular. Hold on just a second. Okay, so it's a popular game. Part of why it's a popular game is there's actually betting involved and people play for money. So a lot of times there are questions of backgammon of like, what's the right way to play this particular dice roll in this particular setting of the board. Often this happens late in the game. So I want to know what's the best, if I roll 5-2, what are the best moves to make? And what backgammon players would do is, if they disagreed, they would go ahead and set up that situation and then simulate several times, right? So basically just play the 5-2 and then roll the dice from then on, playing a fixed strategy from then on. So differing in how they played the 5-2 and then playing everything else the same way and see which one came out ahead. And then of course have to do that simulation several times. And there's something similar that also happens in poker, right? Where two poker players may disagree on how you should play some particular hand. And so what they will do is deal out a number of different simulations and see which one ends up better or not. Okay. These days, we don't physically roll the dice to do these multiple simulations. Instead, we just put it on the computer. Okay. So a rollout algorithm says basically, we're going to have some state we start with. Okay. And we have some potential actions. Action 1, let's just look at 3 actions. Action 2, and action 3. Action 1, action 2, and action 3, lead to new states. So let me actually fix this diagram. So the actions lead to new states. And then from those states, we go ahead and do some simulations. Okay, some sort of a rollout where basically we just follow some policy and for the stochasticity, right, use some pseudo-random number generator and then find out what the rewards are. So we have, you know, R1, R2, R3, R4, R5, 6, R7, R8, R9, R10, R11, R12. And then we just basically look at what is the average reward after having taken action 1, the average reward for having taken action 2, the average reward for having taken action 3, and the one that's highest is the one that we'll use. Okay. Now, do we have 4 rollouts? No, often the rollouts are many more, right? There might be 1,000 or 10,000, something like that. And these all get rolled out, right, until we get to a terminal state. So we can look at our total reward. Okay. In the case of a game, very often we get no reward, you know, chess, checkers, tic-tac-toe, until we get to the terminal state, and then we get our single reward there. Okay. So what we are doing here is starting with a rollout policy. And this is just a policy, right? So it's a policy that tells you what to do in a given state, what action to take in a given state, right? With what probabilities. What the rollout algorithm does is it improves. And I'm going to say it improves the rollout policy. Really what it's doing is it's improving the current action choice of the rollout policy. So often when you're using these rollout algorithm, you're not permanently improving the rollout policy. Instead, you're taking the rollout policy as fixed and you're saying, okay, given that this is the rollout policy, it says for state A that I should take action 2, let's say. This is action 3. So it may be that policy says in the start state, it says to take action 3. And it may be that after we do this rollout, we find that actually action 2 is better. So we have made an improvement to the policy for this given state and no other state. Okay. Does that concept make sense?
This is a question not, I guess, specifically pertaining to this policy, but when you're discussing like the potential of going down all these different branches and then eventually hitting like a tie, for example, I was wondering if it's uncommon to, you know, either have like inflated rewards or deflated rewards so that the relative rewards are still the same, but I was worried that you know, we might lose a lot of work if maybe at the beginning we don't get any updates because a lot of our rewards are just 0. So is that something that's uncommon to just, you know, make all the rewards artificially high or artificially low while maintaining like a relative ratio?
So if we look at so we shouldn't really make much of a difference whether we do relative values or not. There are a couple things I guess I want to talk about. So one thing I want to talk about is the fact that we commonly will want to make the, if we're doing a game, we will want to make the winning for one person be negative the winning of the other person, right? So +1 for player 1 winning and a -1 for player 2 winning. So, and a 0 for a draw. If we change it from +1 -1 to +100 -100, nothing really is gonna particularly change, right? If we tried to shift it up, that will cause some difficulties in terms of changing the player 1, player 2 values.
Right.
So we could end up with a lot of draws. That's certainly the case, and that's one of the reasons we're doing a lot of rollouts, is to try and ensure that some of our terminal states don't end in draws. Okay. Here's the odd thing about the rollout policy that's often used. So often, rollout policy is uniform random. Okay. So clearly, that's not particularly good, right? But surprisingly, just deciding what action to take by saying, if I took that action and then I randomly took moves from there, right? So player 1 has random moves, player 2 has random moves, that'll lead me to some position that still tells me something about whether this is a good place to be in or a bad place to be in, right? Whether this ended up as a good state or a bad state. I'll show you that. Let me actually just show you that concept right now. So my claim is, let's say we are in a state not with a blank slate, right? So we've actually, X and O have both made some moves. So let's say we do X, O, O, X. Okay, so that's our state. Now, we all know that blocking O is a good thing, right? But how could a random algorithm using a rollout policy figure that out? Let's just look at that. Okay, so we're starting this state. It's X's turn, and we need to decide what to do. Well, there are 5 different possibilities that we need to consider, right? Each of the 5 possibilities of where X could go. X could go here. Okay. And if X goes here, then let's just look now at a random rollout of this. Okay. But let's kind of assign probabilities because we can see what's going on here, right? What percentage of the time would O win on the next turn, Mark? So on the next turn, what percentage of the time would O win if they're playing randomly?
Just 1 out of 4.
Yeah, 1 out of 4. So I'm going to put the rollout all in red. So we have here, so this is a terminal state, which is X, X, O, 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 X, right? Terminal reward equals -1, because this is all from player's 1 point of view. And you and I happen to know that that happens 1/4 of the time, right?
Mm-hmm.
So 1/4 of the time, we're going to get a reward of -1 if we play this red X. Another 1/4 of the time, we'll end up, let's say, as let's say O plays here, right? And then, so this is a 1/4 of a time. And then a 1/3 of the time, we'll win on the next play, right?
Mm-hmm.
And we've got other possibilities that happen as well. But these do kind of reflect the fact that this is not going to be a very good move. Because if we run this multiple times, we're going to find a 1/4 of the time we get a -1, 1/12 of the time we get a positive one. Much of the time, we're probably going to get a tie. And so we're going to end up as some, the average is going to be some negative value. Would you agree with that?
Yeah.
Okay. Now, another possibility is we go here, right? Which we all know means blocking O. But as far as this rollout algorithm is concerned, all it does is it just tries all 5 possibilities, right? So this is another possibility. And here, what is our guess as to what we're going to end up with if we do a bunch of rollouts? So is probably a lot of draws, I'm guessing. And there are some cases when O wins and some cases where X wins. So I'm going to predict that the average is 0 to slightly positive. Just because X has more ways to get 3 in a row than O has ways to get 3 in a row.
Mm-hmm.
Right?
Yeah.
And we can continue on there and see what the other possibilities are. And do all these rollouts. And then figure out that we should choose the highest value we've got for this second level, right? And that will be the action we'll take. And I'm going to predict that that's going to be blocking O, right? That'll be better. So what we're doing here is basically saying we can come up with an estimate for how good it is for X to be in this position, right, in this state. And the way we can come up with that is just randomly fill in X's and O's, okay? Because it does reflect the fact that this is a better state than this state is. Because if we randomly choose X's and O's, it's very easy for O to win, right? And if we look at this state and compare it to, let's say, XO, XO. Oh, I was going to say X in another spot, but my guess is that probably, just looking at it, I'm going to guess the rollouts would be such that this second action of blocking the O's is a positive, 0 to slightly positive action. And all of the other 4 actions are probably very close to one another, if not identical. Okay. Mm-hmm. And all negative. So what we're doing then with the rollout algorithm is we are improving, in this case, the random policy. Okay. And the planning that we're doing is planning at a single step, at decision time. So it's time to play a piece. Let us go ahead and do this rollout algorithm and figure out what piece we're going to play. And then once that piece is played, there's a decision to make of the next piece to play, and we would do the whole rollout algorithm again. Just throw away all that information we've done and rework. Okay.
So Prof. Rhodes, so why is it? So why would we throw everything out? It seems kind of useless if we just each time we reach a certain state to just throw everything out.
That's true. We will look at some ways in which we can save some information. Okay. But right now it's just what's the simplest thing that could possibly work. Okay.
Okay, got it.
So the Monte Carlo tree search uses kind of the same idea as rollout, except instead of just coming up with one level and then doing rollouts from there on out, we build up the tree more. Okay, so we go ahead and build up the tree in a principled way, where we might say, okay, the left one looks promising, so we're going to go down and expand out the left one. And maybe also expand out this one. And then maybe we'll expand out this one, and so on. And then go ahead and do rollouts from here. So rather than rolling out just from that first level children, we're going to expand our child nodes more in a way that we're going to have to describe. And then we'll roll out from the leaves of those conceptually. Okay. So we're going to be looking ahead more, right? Because in the case of the simple rollout algorithm, our look ahead is just one step look ahead. And here, in some cases, we can go to 2, 3, 4, or even deeper look ahead for promising avenues. Okay. So we're going to call this the expanded tree. Okay, and so what we do is go through 4 stages. We select a leaf node in the expanded tree. Okay, we're going to talk in more details about those. We then expand one of the children. So every step along the way, and this is in this repetition, we're making the expanded tree one node bigger. So we find a child, we expand in that child, and then we simulate from there. So the way I showed this was kind of we build out the tree and then we do a bunch of simulations. That's not really true. Really what we're doing is doing a simulation every time we add a new node. So we might say, in a way to be determined in a moment, that we're going to expand, we're going to select this node here, okay? And then we expand it. That is, we take one of the actions that we haven't yet chosen from that state and create a node for it. So this is an action. This is a new state. And then we do one simulation. Okay, one Monte Carlo run all the way down to terminal node. Okay. So that's selection, expansion, simulation. And then the backup says, take whatever this value is, this reward, and update each of the nodes from the root up that took us down to this rollout. So we're not updating anything in the reds. Instead, we update, 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 and update. Okay, and this is going to give us some better estimates of the state values of each of those updates. Does the concept kind of make sense? Or are there any questions about that before I go into the details? So by the time we're done, we will have done a rollout from every node in the tree. Okay. So let's look at this selection. So we're trying to go through and figure out what is a most promising avenue to take through our tree. In particular, let's say we're at our root node. So we're looking at the root node and we want to say which of our children is best. Okay. Well, how do we decide our best child? Well, we'll keep 2 pieces of information. we're going to keep for every node, we're going to keep track of what is the total reward we've gotten for it and how many times have we done simulation. So basically this gives us an average reward, right? This is the average reward for V. Okay. As we come back here, when I look at updating here in the green, what update really does is update Q and update N. Okay. So it gives us, all it is allowing us to compute what is the average reward for that node. Okay. Why not just use that? So let's look at, let me add a new slide. So if I've got a state here, and I've got the children here, and these all have state values. Okay, all the children do. Why don't I just want to pick the child with the highest state value? Kaki.
Because you might be missing out on the other states.
Well, let's say these are the only state, the only children that exist from this state, right? So these are all possible actions from this state. And I have done one simulation from each one and come up with an estimate of the value of that state for every child. Why wouldn't I just want to pick the highest one?
Because there might be other simulations that you just haven't seen.
Exactly, right. So this is the difference between exploitation and exploration. So it is exactly similar to the bandit problem. If we look at each of these children as one action to choose, right? We've got some reward from it. Do we want to just be greedy and take the highest reward we've got? Or do we want to take into account that we may get different rewards in the future? So this is the exploitation. If you remember the upper confidence bound, this is exactly upper confidence bound. It's called upper confidence bound for trees. And this is the exploitation. Exploitation. And C is, think of it kind of as our trade-off. How much do we want to prefer exploitation versus exploration? So the idea is, if we haven't visited a child very much, as compared to the number of times we've visited its parent. By visited, I just mean, let's say, simulated, okay? So if we haven't explored much for the child compared to its parent, then we want to increase our bonus as we're determining whether to choose that child or not. And if we have done it a lot, then the bonus doesn't count very much. Okay, so it automatically reduces the exploration bonus as we have tried that child more and more. So we're going to use UCT to pick one of these children. And then, assuming that guy has children, we will go ahead and figure out which child to use in the same fashion. Okay, and we'll keep going, and we keep going until we get a node that has unexpanded children. Okay, so if we've got a node and there's a child, there's an action that we've never tried from that node, we stop. That's our selected node. Right. So let's say we're first starting this. So we're first starting Monte Carlo tree search. Shannon, what node are we going to select?
Top node?
The top node, right? They're for two reasons. One, there's nowhere to go. There's nothing else in the tree yet. And second, it has children we haven't tried yet, right? Well, we assume that there are actions we can take to give us children. which action should we try? Yeah, so we pick a random child. Sorry, we pick a random action. Okay, so first, select this node. That's part one. Part two is expand. So expand says, pick a random child. Sorry, a random action, and create a child for it. So if we look at the case where we have XXO, let's say that is our root, okay? Because the root doesn't necessarily need to be the initial start state. This is just the state we're in now, okay? We want to know what should we do now. This is our state. We select this state, okay, because that's all there is in the tree, is this root node. And now we expand. We randomly pick an action. It would be uninteresting if we picked X to complete it, so we'll pick there. Okay, now we're expanded. So selection, we use upper confidence bound, continuing until we reach a node that has actions we have not yet tried. Once we've done that, we expand. So assuming it's not terminal, because if it's not terminal, there's nothing more we can do, then we choose an untried action and create a new node. And then the next thing we do is do a simulation. So from here, we selected, we expanded, and now we do a simulation. Nelson, when do we stop the simulation?
When you get to a terminal state?
Yeah, we get to terminal state. So we're going to get here, we're either going to have +1, -1, or 0. Let's say in this case, we get +1. Okay? Then the last thing we need to do is back up. That is, we need to back up action value to nodes in the tree. When I say nodes in the tree, we skip all the red things, right? These don't count. These were just rollout states we happen to get to. We don't care about those. We want to do this guy and this guy. So Nelson, so we need to update N and Q. What's N of this state going to be?
1.
Yeah, 1. We're going to just increment it. So it's going to be 1. And Q is going to be?
Is it discounted or is it just 1?
It's just going to be 1. So we're not going to do any discounted for this problem. Okay. And we need to go to its parent too, because we need to go all the way back to the root. So the root, what's it going to be?
Also 1?
Also 1, because this is the first time we've ever updated anything about it, right? And Q is going to be?
Also 1.
Yeah, you might think so. So not quite.
Oh.
Because of the fact we're switching off X's and O's positions. And so what's good for X is bad for O. So here, this green guy was chosen because it was X's turn, right? So this is X's play. Hold on a second. Let me make sure I get this right. So yeah, so that one is going to be a +1. We're going to toggle it every other time as we move up the tree. So this one is actually going to be a -1. So if this guy had a parent, if the root had a parent, from the root's point of view, it's O that's going now, right? And it turns out that this O move wasn't very good because X ended up winning. And so it's a -1 because it's bad.
Oh, I see.
From most point of view. So we're going to update N and V, and we have to adjust the reward again. If the reward is +1 because player 1 won, then whenever you have a node that you get to from player 1 moving, you want to increment that Q. But if it's one that player 2 moved to, you want to decrement it. Okay. And the reason for that, originally I talked about doing a min-max, where you look at mins and then maxes and mins and then maxes. Well, notice back in the selection phase, we're going to just do maxes for every level. And so since we're going to do maxes for every level, we've got to go ahead and negate the Qs so that the max of negated values gives us the min that we want. All right. So we could have fixed this in either the selection or in the Q values in the backing up, and we chose to do it in the Q values. Okay, so, sorry, let's see. So here we are. Let's say Justin. Now we're going to do our next step of MCTS. So we're going to do it again. What would we choose to do?
Sorry, could you repeat the question?
Yeah. Where are we going to start? So we have, again, there's 4 phases: selection, expansion, simulation, and backup. So we're in the selection phase. So we need to select a node in the tree to expand. Mm-hmm. Which node would we select? And again, we're in this here.
I think probably just like the root of the tree. But.
The root of the tree, and here's why. Because there's still actions we haven't tried, right? And so therefore, you stop at a node that has untried actions. And until you've fully filled out the node to have tried all actions, you don't go any lower. Mm-hmm. So we would now go ahead and we would expand to XXOO, and we'd expand to, I don't know, some other value of X. Let's get lucky. Let's choose that one, okay? There's no rollout that has to happen here, right? The rollout just fizzles right away because it's a terminal node. What's the reward? Continue with you, Justin. Who won?
X is 1.
X is 1, so that's a positive one because they're player 1. Mm-hmm. So reward is player 1, and now we need to update N and Q. What N and Q are we going to update?
We're going to update.
And I'll help you out. We start where we started the rollout, and then work our way back up the tree. So where did we start the rollout?
Sorry, I'm a little lost right now.
That's okay. So we expand. So basically, we select and we expand, right? Mm-hmm. Once you've expanded, you go ahead and do a simulation. In our case, the simulation is very simple because the expanded node is, right, this node here is already a terminal node. So we don't even have to roll any dice. We just look, we see we won. Now we update, we back up the expanded node and its parent and its parent and so on. So we're going to start at the expanded node, backing up our +1. So for the expanded node, the question is, what's N equal and what's Q equal?
Would N be equal to -1?
N is just the count of the number of times.
Oh, sorry. N would be equal to 1 then.
N equal 1. And Q?
Q would be equal to, would it be 0, I think?
Not be 0. So whose move was it that got us to this state?
X's move.
X's move. So X moved, and did X do good by this?
Yes.
So therefore, we keep it as positive.
Oh, okay. So Q would be 1 then.
Yeah, Q would be +1. And now we got to go to the parent, right? Mm-hmm. And so here, how are we going to update N?
N is going to be 2 now.
Right. And Q is going to be?
0.
No, because since we just went up another level, mm-hmm. now we're looking at it from O's point of view.
would be
because
-2.
yeah, because O was the one that played
see.
got us in this state.
Yeah.
And now it'll be -2. Okay. So if we look at x's, sorry, if we look at the root node, we can see we've expanded 2 children. We know their values. We have got an n of 1 of each of those. We've got to finish expanding those children. Once we've expanded those children, then we'll pick our best one. Okay, so let's say that what we have is, we have that same starting XX, OO. We've done all 5 of them. And we have, you know, n equals 1, q equals 1, n equals 1, q equals 0, n equals 1, q equals, I don't know, -1, n equals 1, q equals 1, and n equals 1, q equals 0. Next time we're going to select a node. What node are we going to choose? And I guess keep going, Justin.
Next time we select a node, we're going to
and this would be n equals 5, q equals -1.
we would want to select would it be one that like increases q, like?
Yeah, what we want is our highest q divided by n ratio.
So probably highest q divided by n ratio would be the ones where q is positive. So.
Exactly, one of those 2. We'll
Yeah.
randomly choose one. And then, let's say we choose the first one. Then the next thing we would do is expand. Okay? All right.
Rhodes, I have a quick. Are we not using the UCT there, or is this just like?
We are using the UCT there. We're just simplifying by the fact that since n is 1 for every child, the exploration bonus is going to be identical.
Got you. Thanks.
Once we went down here, though, right, and did our simulation, and then we would update n equals 2 here and n equals 6 here, then it may be that our exploration bonus is going to start getting, in fact, let's say we update that. So n equals 2, q equals 2. The next time we visit, the next time we run MCT, we'll choose this guy because q over n equals 1. Q over n equals 1 here too. But the exploration bonus will be bigger here because n is 1 instead of 2.
Rhodes, can you go back to the previous slide when you have a moment?
Yep.
So these 2 states that you've expanded here, they look the same on the surface because they have the same n and q values, but it seems to me like the right state, the one that you have in black, would be maybe more advantageous, right? Because it happens sooner, right? Like we win sooner. Does this model have any way of capturing that?
Nope. But here's what will happen, right? As we start doing more simulations that happen to go through these nodes, we'll find that the black one on the right every time gets a 1, right?
Right.
And on the left, we're not always going to get a 1. We just got lucky the first time. Sometimes we'll get a 1, sometimes we'll get a draw, sometimes we'll get a -1.
Okay, I see.
Okay, so as we do more simulations, we'll get a more accurate picture of what that q over n should be.
Got it. Okay, awesome, thank you.
Yeah, sure. Okay, let me quickly finish up and just say, when we're done, we need to figure out, right? The reason we did all this is to figure out, hey, this is what the current board looks like, right? The current board looks like XXOO. What should I play? So you're gonna have to make that decision. The way to make the decision is to, you can use UCT as well if you want, but UCT would use exploration, and you probably don't want to explore, right? You were doing this exploring to figure out what the best action is. Now you have this measure of which is the best action. Okay, so just look at the highest average reward. Okay, That has one potential problem though. What if many states had a high N, and we had one state, or one state that you get to by an action, with low N but high Q? You know, maybe this was the last action you tried, and it happened to have you tried it once, and it happened to reward you really well. Well, was that just a fluke or not a fluke? So an alternate that you could use, instead of just choosing the highest average value and having no exploration bonus, would be just choose the child that you visited most. And the theory here is the child you visited most is the one you spent a lot of time exploring. And the reason you spent a lot of time exploring was because it was good. And the fact that it's a high N means it also has a low variance, right? So it's probably fairly accurate. Either one of these will work. Often, this is the one that's used. I have one question for you guys. Maybe you could just vote up or down. My question is, I'm again handing out the PDF of the midterm on Monday. It'll be due on Wednesday. For Monday, I can either move forward in new material, or I can do a review lecture. Can I just get a thumbs up for, let's say, review lecture? So thumbs up is review lecture, and thumbs down is new material. I am sensing a theme, and so we will have a review lecture on Monday. Please come with questions. Varun asks, couldn't high N of V mean that there were just a lot of children? Yes, it means, in fact, that there were a lot of children. But why were there a lot of children? Because many times we decided that child is a good child to go down. It's the best child at the time, right? Using UCT criteria. So N got high because many, many times that was the best UCT to choose. Does that explain that, Varun? Okay. All right. I will have office hours until 3:30. Just hang around if you want to talk.
So one quick question about the rollout.
Go ahead, Masta. Yep.
So each time we do a rollout, we just explore like one trajectory and increment our N by 1. Is that correct?
That's right.
And then how do we assure, I guess, so the way that we make sure that we keep trying new things is we have like another sort of round of UCT for that node's children when we're doing rollout, or how is it that we make sure that we try different things instead of just keep on doing the same thing when we visit that node?
Yeah, every time we're moving from starting at the root and moving our way down to select a node, we're always using UCT. Okay,
Gotcha.
so it's UCT from the root to its child, and then from that child, it's UCT down to its children, and so on, and so on.
Cool, thank you.
So, yeah, so we always have some exploration built in there. You're welcome. All right, I'm gonna go ahead and stop the recording.